Hi, Dr. Revis here. In this video, I will show you a short lecture on molar ratio usage from balanced equations and molecular formulas. Let's do this by considering the double displacement reaction shown here. We have phosphorus pentachloride plus water given phosphoric acid plus HCl. That is the original equation. That equation must be balanced. It can be balanced by adding a coefficient of 4 in front of water and a coefficient of 5 in front of HCl. Once you have the balanced equation, which is perhaps the most important step in this entire problem, but once you have the balanced equation, then you can proceed to answer the questions. So, question number 1. What mass of hydrochloric acid is produced from the reaction of 14.21 grams of water with excess phosphorus pentachloride? To do this, we set up a standard dimensional analysis, starting with the given. The given is 14.21 grams of water. We do cross hash of 18 grams of water on the bottom, moles of water on the top, and then since we're going from water to HCl, that is from one species, one compound to a new compound, we must interconvert using the molar ratio of water, mole water on the bottom, to mole HCl on the top, and we get the units for this from the balanced equation. So we have 5 moles of HCl per 4 moles of water. And then we continue with the dimensional analysis. Moles of HCl go on the bottom to grams of HCl on top, and we get 35.95 grams of HCl. Remember that in going from one compound to a new compound, we use the balanced equation molar ratio. Let's do problem number 2. What mass of hydrogen is consumed in a reaction with 14.24 grams of water is reacted with excess of phosphorus pentachloride? Note here that in the balanced equation we do not directly see hydrogen, so we use an indirect source of hydrogen, which in this case is water. When you're using an indirect source of an atom or element, you will use the molecular formula in your dimensional analysis. So let's carry it out. We have 14.24 grams of water. We do times 18.015 gram water to mole water as the first conversion factor. Then that's times the mole of water to ratio of hydrogen, which is 2 to 1 based upon the molecular formula. So in other words, when the species of interest or the element or compound of interest is not directly shown in the balanced equation, you will more times than not use the molecular formula to determine the ratio for this conversion factor. Then we complete the conversion factor with a mole or gram per mole of hydrogen to give you 1.59 grams of hydrogen. So what's the difference? In problem number 1, we have a balanced equation where we're carrying one compound to a new compound. We use the balanced equation coefficients. In the case of problem number 2, we have an indirect measure of hydrogen through water. And since it's an indirect measure of hydrogen through water, we use the ratio of hydrogen in water from the molecular formula for the conversion factor. Note on the bottom of the slide here that we have the molar mass that we anticipated using for this problem. Let's do problem number 3. What mass of phosphorus pentachloride is produced from the reaction with 14.21 grams of water? So we again start with the given grams of water. We do a dimensional analysis of converting grams to moles of water. And then we are going to interconvert water to phosphorus pentachloride. Therefore, we will use the ratio from the balanced equation of mole water to mole phosphorus pentachloride. We look at the balanced equation and we see 1 mole of phosphorus pentachloride in the equation and 4 moles of water. We continue the dimensional analysis of times the mole phosphorus pentachloride on the bottom to gram, which is the molar mass, gram per mole, and we get 14.06 gram phosphorus pentachloride, which has 4 significant figures to match the given significant figures. Let's do problem number 4. And in problem number 4, we're going to show you how both these conversion factors can be used. What mass of chlorine is consumed in the reaction of 14.21 grams of water is reacted with excess of phosphorus pentachloride? In this case, chlorine does not appear in the balanced equation. Therefore, we must use an indirect method of finding the chlorine. In this case, chlorine is found in phosphorus pentachloride. Therefore, let's carry out the dimensional analysis with this in mind. So we have 14.21 grams of water converted using 18.015 grams of water per mole of water times mole water on the bottom, interconverted or converted to moles of phosphorus pentachloride. And we look at the balanced equation for the ratio of phosphorus pentachloride to water, and that's a 1:4 ratio. Note that we do not see the 1 in front of the phosphorus pentachloride, but it's assumed to be 1. It is always 1. We just don't write the 1s in chemistry. We continue now because we're going to convert the phosphorus pentachloride into chlorine. So we would then use the molecular formula because we do not see chlorine directly in the balanced equation. Therefore, we know that we must use the ratio from the compound where chlorine appears, and it appears as a 5 in that compound. So we have a 1:5 molar ratio, then we do a gram per mole conversion, and we get 34.956 grams of chlorine. So the take-home point here, or the point to make sure you remember, is that when both species are present in the balanced equation, we would then use the coefficients from the balanced equation as a conversion factor. If the species does not appear in the balanced equation, it is then an indirect source that we must use. And when we use an indirect source, we would then look at the molecular formula for the ratio of the compound to the atoms in that compound. There you have it, a short lecture on molar ratio usage from balanced equations and molecular formulas.